All right, I know in the past few videos we've covered a number of various gas laws, but these are the last two, I promise, at least that we'll cover in this course. The first one we're going to look at in this video is called Dalton's Law, and then we'll follow up by talking about Graham's Law. But let's talk about Dalton's Law first. So Dalton's Law is pretty straightforward, and Dalton's Law says that the pressure for a mixture of gases is equal to the partial pressures, the sum of the partial pressures, excuse me, for all gases present. All right, and I know this sounds a little bit weird, but imagine it this way. It's basically saying that PT is pressure total. And you maybe have a mixture of gases. I'll call this gas pressure of A, pressure of B, pressure of C, and so on. So this would be the partial pressure of A. And then you'd have partial pressure B and so on. So it's this cool additive thing. And I will make a note here that this assumes the same temp and volume. All right. And volume, because we know if we change either of those, if we change the temperature, we're going to change the pressure, and if we change the volume, we're going to change pressure as well. We saw those in our other gas laws. All right, so let's take an example. So in this example problem, we'll take a sample of air, just, generic air from a room. And this sample of air has the following gases. These are going to be the main ones that we're going to worry about. We've got oxygen in the room, which is good. We need that to breathe. We've got a lot of nitrogen in our air, and we've got some water. However, this water is going to just be gaseous water. Really, this is the same thing as saying you've got humidity in the air, right? Water can exist in the gas phase as well. All right, the total air pressure is 742 torr. Torr is one of those pressures we saw as being a commonly used one for gas laws. So we're going to practice using torrs. All right. And then the partial pressure of oxygen was measured to be 141 torr. In fact, we're just going to abbreviate that as PO2, as partial pressure, right? So we'll just say, as a note, partial pressure. All right, we could do the same thing with nitrogen. And nitrogen could be measured at 581 torr. However, this chemist might be trying to figure out, well, if we know that, what's the partial pressure of water? Okay, so we are working with partial pressures here, but this isn't too bad to solve because we know that pressure total should be equal to the partial pressure of oxygen plus the partial pressure of nitrogen plus the partial pressure of our gaseous water. Okay, so if we rearrange this a little bit, we could say, well, the pressure of H2O is going to be equal to the pressure total minus the pressure of O2 plus the pressure of N2. Sorry, this should be in brackets here. Okay, so let's go ahead and plug that in. We know we've got 742 minus our partial pressure of O2, which was 141, plus our partial pressure of nitrogen, which was 581. And that tells us that the partial pressure of water in this case would be equal to 20 torr. So it's a useful tool for finding out let's say, a missing component of a gas mixture. If you know all of the other variables, solve for the variable you don't know. In this case, we were just solving for the partial pressure of water down here. All right, so I hope that makes sense. It's a kind of generic one. I will say the ideal gas law is the most commonly used one, but this one will occasionally pop up. So that's one of the last ones we want to look at, but we've got one more. We've got Graham's law. And Graham's law is a little bit different than Dalton's law. And what it does is it describes the rate of diffusion or effusion. Don't worry, we'll define diffusion and effusion here in a second. Of two gases to the relative molecular weight, and I'm just going to abbreviate that as MW, of the gases. Okay, so let's take a look at Graham's law first. So rate of gas A relative to the rate of gas B, and this rate could be for diffusion or it could be effusion. Doesn't really matter which one. It works for both of these equally well. And these rates can be presented as a ratio, just like we've been talking about. So how fast does one gas diffuse relative to another gas? And for the other side of this equation, we're going to take the molecular weight of gas B divided by the molecular weight of gas A. So as you can see, the A's are actually on opposite sides, and the B's are on opposite sides. But this is a useful law for figuring out diffusion and effusion rates. Okay, so now let's define those two terms because they are kind of subtle. So diffusion is a process that causes gases to mix. So let's just write this down. So it's a spontaneous process that causes mixing of gases. The way I like to describe diffusion is imagine somebody sprays perfume across the classroom from you. Over a period of time, you'll eventually be able to smell that perfume. The question is why? Well, it's the diffusion process. Those gas molecules in the perfume will eventually just kind of work their way over time in order to form an equilibrium whereby they spread around the entire room. So that's how I remember diffusion. Effusion, I know it sounds really similar, is a little bit different. It's the process through which gas escapes a container through a small hole. So you can imagine, let's say you've got a box containing oxygen and you poke a hole in it. Some of those oxygen molecules on the inside of the box will just kind of sneak out of that hole over time, right? That's effusion, which is different than diffusion. So I just wanted to kind of differentiate these. But both of these are basically looking at the phenomena of gas moving around spontaneously, right? In the first one, we're looking at mixing, and the second one, we're looking at it escaping. But it's the spontaneous movement of gases. Okay? So let's consider the following example. So let's consider two identical cylinders. Okay? We've got one with O2 and the other with helium. Both have the same pressure, temp, and identical tiny leaks. Which will leak faster? Okay, so this is kind of a weird word problem, but let's just break it down, and we'll say that O2, in this case, I'm going to just identify as A, and I'm going to say that helium is going to be identified as gas B. Okay, and we said that the rate that A escapes versus the rate that B escapes is going to be equal to the square root of the molecular weight of B over the molecular weight of A, right? So now we can start plugging things in. And I'll just say that the rate of oxygen escaping over the rate of helium escaping is going to be equal to the molecular weight of oxygen. So we'll just rewrite this using more plain terminology versus, oops, sorry, this should be helium, excuse me. And the molecular weight of oxygen should be down here. So now we've kind of more clearly defined that equation. So again, we could say, well, the rate of O2 escape over the rate of helium escaping is going to be equal to, whoops, that should have been He up there, to the molecular weight of helium, which is 4.003, divided by the molecular weight of oxygen, which is 32.00. And if you plug this into your calculator, you should get 0.3537, which another way of writing this all out is we could say that the rate of O2 escape over the rate of helium escaping, whoops, is going to be equal to 0.3537 over 1, right? So you could think about this and you could say, well, looking at this, it looks like O2 escapes approximately 3 times slower. All right, if you want to really get mathematical with it, we could flip things upside down. So let's just imagine flip this and flip this. And if we want to do that, another way of writing this is we could just invert it. So we could say, okay, the rate of helium escape over the rate of oxygen escape is going to be equal to 1 divided by 0.3537, which if you plug that into your calculator, take 1 divided by 0.3537, you're going to get a number that's 2.827, and that's the same thing as writing it over 1, so it's another way of saying this exact same thing that we said above, is that helium escapes 2.827 times faster. All right, and you might be wondering, all right, this is great. I could see this being used in really niche circumstances, but why? Why is this happening? Well, if you think about the mass of helium, right, it's a lot lighter. And if it's lighter at the same temperature, that means it's going to be zipping around at a faster speed, right? Because it doesn't take as much energy to move around lighter molecules. So it's going to be zipping around at a faster speed, which is going to cause it to spontaneously escape from that tiny hole a lot faster. But the cool thing with this law is he found this mathematical relationship with how quickly this process occurs. But it's only useful as a relative rate comparison for diffusion and effusion. All right, I hope that helps. But if you have any questions, let me know.